Hello everyone, welcome back to HealthGIS channel. In this video tutorial, we're going to explore how to analyze matched case control data in R, which is critical in epidemiology and outbreak investigations. By the end of today's session, you should be able to understand why we match cases and controls. Then we will use McNemar's test for one-to-one matched data and then calculate matched odds ratio and its confidence interval for this test. Then we will move to 1-to-m matching using Mantel-Haenszel method. And finally, we will use conditional logistic regression, which is more flexible and used for more complex match design. Let's get started. So what is matching and why do we match? In the previous video, we learned that in observational studies, confounding can distort the true relationship between exposure and outcome. Matching is a specific study design strategy that is used to control for confounding. In matched case control studies, each case is paired or matched with one or more controls who share similar characteristics like age, sex, income, race, residence, and so on. So the question is, what happens when you match on age? If you match based on age, both groups will have the same age distribution, which makes the comparison fair by removing age as a confounder. So you can match based on any variables you believe can confound the association between exposure and outcome. But remember that we only match on confounders, not on risk factors or variables on the causal pathway. Also, matching can introduce selection bias because we are intentionally choosing people to include. But that's often acceptable as long as it helps reduce confounding and makes the comparison fair. We have two types of matching. One-to-one matching means that for every case in a study, there is exactly one control who is matched on specific variables like age, sex, location, race, and so on. And one-to-m matching means that for every case in a study, there are two or more controls who are matched on specific variables. So let's first begin with one-to-one matching. So we use one-to-one matching when you have limited resources or control data, or you're doing a small scale study or pilot investigation, or you want to simplify the analysis. The most common method for analyzing one-to-one matched cases and control is McNemar's test. Before running the McNemar's test, we have to understand what it does and prepare the data accordingly. McNemar's test is used for matched case control studies with one-to-one matching or before-after studies. The required data type is binary, for example, yes or no, exposed or not exposed, cases and control, and focuses on discordant pairs, where case and control differ in exposure. So we have to create a table like this, that the cases are on the rows, as you can see, exposed and not exposed, and controls on columns that are exposed and not exposed. And each cell here, E, F, G, H, each cell represents a type of matched pair, okay? So instead of counting individuals, we count matched pairs. For example, E here represents that the case was exposed and control was exposed as well. Or F here represents that the case was exposed but the control was not exposed. So in this table, we are especially interested in discordant pairs. So these are the pairs where the case and control differ in their exposure. So cell F includes pair where the case was exposed but the control was not, and cell G represent the control was exposed but the case was not. So both F and G are important because they show a difference in exposure between case and controls. So the other two cells, E and H, are concordant pairs, and both the case and controls were either exposed or unexposed. So these pairs do not contribute useful information when calculating the odds ratio because they don't show a difference in exposure between case and controls. So to estimate the odds ratio in this design, we use only the discordant pairs and apply the simple formula F divided by G. So that gives us the odds ratio. The null hypothesis here states that there is no difference in exposure between cases and matched controls. An alternative hypothesis that there is a difference in exposure proportion. And if we get a significant p-value, for instance less than 0.05, it means that the exposure differs significantly between cases and controls in discordant pairs. So you may ask, what is the difference between McNemar's and chi-square test? So chi-square test assumes independent observation, but McNemar's is for matched or paired or dependent data. And the limitations of the McNemar's test is that it only works for two categorical or binary outcome, and it's only used for one-to-one matching and doesn't tell you the strengths of the association or confidence interval. That's why we have to calculate the odds ratio and confidence interval. So the data set that we are using for this one-to-one matching is blood clot or Pills clot data. So the exposure variable here is actually birth control pills, shown by pills here. So the value of 1 means that the people, they use oral contraceptive birth control pills, and the value of 2 means that they didn't use this birth control pill. And also for the outcome, so the blood clot, this is our outcome. The value of 1 here means that they have the outcome or the person is a case, and the value of 2 means that they were controls or don't have blood clots. So, and also ID here is used for matching. For example, these two, they have been matched. Why? Because they have the same ID, but this one is a case. This person is a case. Why? Because the blood clot is 1, but this one is a control. And both of them have been exposed to the birth control pills. So how many matched cases and controls do we have here? So we have 175 matched pairs of cases and controls. So let's open up RStudio and load the data. Okay, so the first thing I'm gonna do is that I'm gonna use read.csv, file.choose, and set the header to true, and save the data in an object called data, and then run. And after running the command, so let's find the data, blood clot, and then open. So as I said, this is a one-to-one matched case control study, which means that for each case we have exactly one matched control. So let's say they have been matched based on gender, race, age as potential confounder. So let's confirm that each ID has one case and one control by creating a contingency table based on ID and the status of the blood clots. Okay, so if I use table command, table, so it's going to be from data, I'm going to select ID and also data blood clots, run. So as you can see, for each ID, so here are these here, and also these are the values for the blood clot, which could be 1 or 2. 1 means case and 2 means control. So for each ID we have only one case and one control, one case, one control. And if you see, for all of the IDs we have one case and one control. So this is a one-to-one matched case control study. And also you can see how many cases and how many controls do we have. So if I just use table command and then data blood clot, so it shows us we have 175 cases and 175 controls. So in order to create the table in a structure that we just saw, we first need to separate cases and controls using the subset command. So subset command in R is used to extract specific rows or columns. So let's subset the one that blood clot is 1, or cases, right? So from data, I'm gonna say that if the blood, I think it was blood underscore clot double equals to 1. So I'm gonna subset this and put this in the object cases. So run. So let's see what happens. So cases, so you can see 175 observation and 3 variables. So all of them are blood clots are gonna be 1, which means that they are cases, right? And also let's do this for the controls. So this one is gonna be 2, and this is going to be your controls. So these are our controls. As you can see, all of them, their blood clot is 2, which means that they are controls. Okay, so after subsetting into 2 groups, cases and controls, the row order may differ between cases and controls. Okay, so especially if the original data set wasn't sorted, if you don't order the data and compare cases and controls without aligning them by ID, you might match the wrong pairs, so which leads to incorrect results. So to address this issue, we have to order the cases by ID. So let's first extract the ID column from cases, And then after extracting it, I'm going to sort this from smallest to largest. So using order, cases, and ID. So we just have sorted the ID value from smallest to the largest. Okay, so, and we are going to use this order to rearrange all rows in the cases data set. So in order to do that, so I'm going to say that, so this is going to be our rows and for the cases data set. So I'm going to use this. So this is going to be our rows, and this is going to be, I'm not going to change the column, right? So this is going to be my cases. I'm going to store it again to the object cases. So this helps us to ensure that all of the rows in the cases file have been ordered by ID. So if I repeat this for the controls, so from control, so order based on order controls by ID, and then again store it in the same object and then run. Now we are confident that both cases and controls have been sorted based on ID column. Okay, so we can now compare the exposure of the cases and controls using the table command. So if I use the table from the cases, so I can compare the pills, which is the exposure for the cases, and also for the controls, I can compare the pills. Okay, so and then I can store it in an object, for example, called tap1 or tap, and then run. So let's look at tap. So how many cases and controls were exposed? 10. How many of them cases were exposed but the control was not exposed? 57. Cases what not exposed but control was exposed. Cases what not exposed and control was not exposed. 95. So now that we have created the table correctly, we can run the McNemar's test. So this test focuses only on the discordant pairs. Okay, so where the case and control differ in exposure. So as I said, the null hypothesis states that there is no difference in exposure between cases and matched controls. An alternative hypothesis states that there is a difference in exposure between cases and matched controls. Okay, so to run the McNemar's test, so I just use McNemar test, and the input is going to be your table that is in this format, tap, and then run. So as you can see, the p-value is very small, which means that there is a statistically significant difference in exposure, which means that there's control pills between cases, which are blood clots, and their matched controls, suggesting that exposure is associated with being a case. But as I mentioned, the McNemar's test doesn't tell you the strengths of the association. We need to quantify the association. Okay, so from this table, I have to select this one and also select this one, discordant pair. Okay, so from tap, it's going to be row 1, column 2. So I'm going to store it in object A, and also from tap, I'm going to select row 2, column 1, and I'm going to save this in object B. So if you run this line of code, A and B, so the odds ratio is going to be A divided by B. So as you can see, the odds ratio is 4.38. We also need to assess whether it's significant or not. So let's calculate the confidence interval for this. So we should, as I mentioned, only focus on discordant pairs, those where the cases and controls differ in their exposure. So these pairs are the only ones that I mentioned, A and B. These pairs are the only ones that contribute information about the association between exposure and outcomes. Here the question is whether the case is more likely to be exposed than the control. So in this context, our success is that the case was exposed, but the control was not. And the failure is that the control was exposed, but the case was not. So A is going to be our success, and B is going to be our failure. And the total discordant pairs is going to be A plus B, which is a binomial problem, and we have to use binomial test to calculate the confidence interval for the probability that the case is exposed. Okay, so we have to use binom.test, and it's going to be A, which is the success, and A plus B is going to be the total discordant pairs. And I'm going to save this in variable P So let's run this code. So this is the P, but P is a list. So I have to extract a confidence interval from this P. So this is going to be the confidence interval for the probability, but we are interested in the odds ratio, the confidence interval for the odds ratio, not the raw probability. So we know that to convert probability to odds ratio, we have to use the formula P divided 1 minus P, right? So that gives us the odds ratio to transform it to the confidence interval. So this is, so let me save this to, I don't know, CI, confidence interval for probability, and this one, CI probability divided by P divided by 1 minus P, CI P. So this gives us odds ratio, CI underscore odds ratio, okay? So we are looking for the confidence interval for the odds ratio, not the probability. So run this line of code and run this line of code. So CI underscore odds ratio. So this is the confidence interval for the odds ratio. As you can see, it never crosses 1, so which means that the results are statistically significant. So the odds of exposure to birth control pills among cases was 4.4 times higher than among controls. It is also significant, and controlling for age, gender, and race, which were our initial confounders that we have controlled for. So when do we use 1 to m matching? So multiple matching is useful when the condition being studied is rare, or you are at the earliest stages of the outbreak, and you have it's very hard for you to find a case, but controls are very easy to find. So you have many more controls than cases. For example, you can get the controls from disease registry or electronic health records. Or sometimes you want to increase the statistical power without collecting more cases. So in that cases, we have to use 1 to m matching. But keep in mind that adding more than 4 controls per case will rarely increase your chances of detecting an association between exposure and outcome. Common method for analyzing 1 to m matched data is Mantel-Haenszel method that we discussed in the last video. Okay, so we are going to use the data that is called nerve mercury, that is between the exposure to mercury and nerve damage. Again, the same coding. So if it was so the exposure is going to be exposure to mercury. If it's 1, means it exposed. If it's 2, it means not exposed. And nerve damage, this is your outcome. If it's 1, means that it's a case. If it's 2, it means that it is control. And here, as you can see, for example, there are 3 cases or controls that have been matched. So there is only 1 case here. For example, you can see ID1. So we have 2 matched controls for it, right? For ID2, we have 3 matched for 1 case. We have 3 matched controls for it, and so on. So let's open up RS Studio and read the data. So I'm gonna use read.csv file.choose and set the header to true, and I'm gonna store it in an object, for example nerve, and then run. So it was nerve mercury, open, and in order to confirm that each ID has 1 case but more than controls, you have to again create the contingency table based on ID and the outcome, which is nerve damage, right? So create a table based on nerve ID and your outcome, which is nerve damage, right? So this is going to be tab 2, and then run. So let's look at the tab 2. So we have 14 matched data, but sometimes for each case, so for example for ID1 we have 1 case but 2 controls. Here we have 1 case but 3 controls, 1 case 2 controls, 1 case 1 control, okay? But we don't have more than 4 controls per case. So let's look at the, for example, table nerve and then nerve damage. So you can see we have 14 cases and 29 controls. So it is obvious that you can't use McNemar's test because you no longer have a direct one-to-one comparison that is required for creating the table or conducting the test. So we don't need to separate cases and controls or sort them and so on, okay? So to address this type of problem, we use Mantel-Haenszel test. So if you remember, the Mantel-Haenszel is used when we want to adjust for a potential confounder using stratified analysis. So instead of looking at just one big table, we break the table into strata of the confounding variable and then calculate its odds ratio within each stratum. And the Mantel-Haenszel method pulls this odds ratio into a single weighted estimate, so which is known as a common or pooled odds ratio. So here we will stratify the exposure to mercury and nerve damage relationship accounted by the variable that identifies the matched sets of cases and control, which is ID variable. So we have to create a three-dimensional table. So I'm going to call this table 3, tab 3. So our tab 3 is going to be for table. So the first one, if you remember, the first dimension is your exposure, which is, so from nerve is going to be mercury. This is your exposure. And the second one is going to be your outcome. So from nerve is going to be a nerve damage. And the last one is going to be your strata of the confounders, right? So which is based on the ID. So what is tab 3? Let's look at tab 3. So here when ID is 1, okay, so when ID is 1, it finds the relationship between exposure to outcome, mercury and nerve damage. Okay, so how many mercury is exposed, not exposed, and nerve damage, yes or no, right? And then when ID is 2, when ID is 3, when ID is 4, until when ID is 14. So for each of these, it calculates the odds ratio here, odds ratio here, odds ratio here, and so on. Then combine it, right? And then combines all of, or pool all of this odds ratio to have a single value of odds ratio, okay? So the stratum that has higher number of the cases, has higher numbers here, it will get more weight in the final odds ratio. Now let's calculate the Mantel-Haenszel test. So if I use Mantel HAEN.test, and the input is going to be your table 3, and then run. So as you can see, first of all, the p-value is significant, and here also the common or pooled odds ratio, which is a large value, 8.28, and also it gives us the confidence interval that never crosses 1, right? So which means that the results are statistically significant. So how we can interpret that? After controlling for matching. So we have, how do we control for matching? Using ID, right? After controlling matching by ID, individuals with nerve damage had 8.3 times the odds of being exposed to mercury compared to those without nerve damage. So we compare odds of exposure between cases and controls after controlling for confounders. And the association, as I said, is statistically significant, and the confidence interval doesn't include 1, suggesting a meaningful relationship. Now let's move on to the most flexible method, which is the conditional logistic regression. Conditional logistic regression is a statistical method designed for matched case control studies when you have 1-to-1 or 1-to-m matching. And compared to simpler approaches like Mantel-Haenszel method, conditional logistic regression is more flexible. It allows you to include multiple covariates, include continuous variables, include interaction, and you can adjust for more potential confounders and explore more complex associations. So the method relies on maximum likelihood estimation, but it does this conditional, meaning that it only uses information from within each match set, which helps control for unmeasured confounding that's constant within match set. So in practice, conditional logistic regression is typically implemented in R using the clogit function from the survival package. And this function allows you to specify your exposure, your outcome, and matched strata, for example, using ID. And outputs will be the adjusted odds ratio along with the confidence intervals and p-value. So let's run the conditional logistic regression on both data. So like logistic regression, we need to recode the outcome to 0 for controls and 1 to cases, right? So if you remember, for if else command, if else has 3 arguments. Okay, so the first one is your condition. The second one is if the condition was true, gets this value. If the condition was not true, gets the third value. So we're gonna say that if the blood clot is case, assign the value of 1. If the blood clot was control, which means that the false, assigns the value of 0. So which is going to be very simple. So from data, blood clot, if it was case, right? So that's going to be your condition. So assign the value of 1 and otherwise assign the value of 0. So this is going to be your, and then I'm going to store it in the same variable, blood. So what happens is that, let's look at the data. Yes, as you can see, if it was a case, assigns the value of 1, if otherwise assigns the value of 0. So we have to also use this for pills, right? So we have to recode the exposure. If use pills, assign the value of 1 as exposed, otherwise 0. So here, if it was 1, assign the value of 1, otherwise assigns the value of 0. And this is also going to be stored in the same object, data pills, and then run. So let's look at the data. So it's going to be only 1 or 0. So now we can run the C-Logit from the survival library. So for the C-Logit, it's similar to the logistic regression, right? So you have dependent variable. So your dependent variable is going to be blood.clot, right? And then use tilde, and your independent variable, which is pills. So if you have more independent variables, you can add and adjust for them, but we don't have. We just need to identify the strata, which is based on ID, right? And the data is going to be our data, right? The data name, the data set name is data. So, and then I'm gonna store it in the variable model 1, run, and then take a summary of the model 1. So as you can see, the odds ratio here is exponent of the coefficient, that's the odds ratio, is 4.38, right? Which is very similar to what we had for the McNemar's test. But in terms of the confidence interval, here there is a small differences because of the rounding or the method that was used in McNemar's test. It was based on the binomial distribution or chi-square test on discordant pairs only, but C-Logit uses the exact conditional likelihood and Wald test. But the p-values for both of them also, if you look at the p-value here, it is significant, right? Here the value is very significant, and also for the McNemar's test. Because C-Logit here uses a model-based framework, you get other, for example, likelihood ratio tests, a Wald test, score test, and as you can see, all of them are significant. Now let's run the conditional logistic regression for the second data set, which was the between the exposure to mercury and nerve damage, okay? So again, we have to prepare the data for the conditional logistic regression. We have to recode outcomes. 1 is going to be case and 0 is going to be control. Again, we have to use if else. If the nerve damage double equals to 1, value is going to be 1, otherwise it's going to be 0, right? So this is going to be recoding the nerve damage. And then run. And also we have to recode the mercury, right? So nerve and then mercury. If it's 1, the value is going to be 1, otherwise it's going to be 0. So nerve mercury, I'm going to store it in the object nerve mercury and then run. So now if you look at the nerve, it's going to be 1 or 0. Okay, if it was 1, still 1. If it was 2, now it's 1. If it was 1, 1. If it was 2, now it's 0. So now we can easily run the conditional logistic regression. So C-Logit, the dependent variable is going to be nerve damage, right? And then tilde, the independent variable is going to be mercury plus strata, which is ID, and then the data that we're going to use is nerve, right? So I'm going to store it in the object, call it model 2, and then take a summary of the model 2. Run and run. So as you can see, the exponential of the coefficient is 7.07, and these are the 95% confidence interval. This is also highly significant. P-value is less than 0.05, right? So as you can see, you got a slightly similar result to the Mantel-Haenszel method. So the odds of mercury exposure among individuals with nerve damage or cases is 7 times higher compared to those without nerve damage or control, adjusting for matching characteristics by ID. So the association is statistically significant because the p-value was less than 0.05, and the confidence interval doesn't include 1, which means that the results are statistically significant. So the difference here that you saw here with the Mantel-Haenszel method is that Mantel-Haenszel method used non-parametric tests, which means that it uses approximation, but conditional logistic regression is an exact parametric maximum likelihood test. So using conditional logistic regression, you can run 1-to-1 and 1-to-m matched case control study. It offers more flexibility and power. You can have more complex models, like you can also add interaction. So if you have more variables, you can add multiplication for interactions. You can add more variables here to adjust for other variables. For example, if you have alcohol use, you can add